All right. So to begin class, we're going to go over and correct your homework from yesterday, which were problems 8 through 17 on the bottom of your chapter 17 worksheet. Turn and talk with the table partner. I'll be coming around to stamp your work in a moment. Be prepared to share your answers with the class as we go through it. Hello.
Hi.
All right, guys. Shh, don't worry about it. You're right now checking. Okay, thank you. Then take out your science notebook. Asian dog.
Yeah, I think it might be. Then again, that means the reaction can happen really fast. So maybe that's not. Maybe it is. Because the jump's so big that it would be.
Go for it. It's just stuffy. I've already sent emails saying, please check this, make this better. But
Yeah, it's been.
it's hard. The temperature is so cold at night and so hot during the day, and we're on the second floor, and I totally understand it, and blah, 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 but it's annoying.
Because there are some rooms that are really cold.
Yeah, it's a huge building. I'm sure it's just a nightmare to manage it. All right.
Yeah, they look better than they did yesterday. Energetic, activated. It might be.
I did. Well, okay. It doesn't matter because that's an independent.
You had one. All right. Here we go. All right, let's go over these. Thank you for comparing with your table partner. Please pause your conversations and be prepared to share your answers. We are using graphs A, B, C, and D in the middle of our page, and we are looking at the statements and choosing which graph most accurately communicates the statement that's written. So for for number 8, for the forward reaction, this graph would show the lowest initial energy state for the reactants. Tyler, which graph shows the lowest initial energy state for the reactants?
I'd assume the first one.
And you would be correct. And Sierra, explain why he is correct in that assumption. Where are the reactants found on the forward reaction? Very good. The very beginning of the graph. So these are the reactants, 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 and reactants in each of those locations. And in graph A, they have the lowest relative energy at 50 kilopascals versus just over 300, 150, and 100. Number 9, which graph shows the greatest activation energy, again, for the forward reaction? So we remember forward reaction means to the right. Reverse reaction means reading it right to left. Yes. Ms. Hamilton, which reaction shows the greatest activation energy for the forward reaction? So we are reading left to right, left to right, left to right. Activation energy is the difference between the reactants and the activated complex. reactants, activated complex, reactants, activated complex, reactants, activated complex. Which one shows the greatest jump? A does. All right. And I'm feeling slightly uncomfortable because A was used twice, but I'm trusting myself because it appears to be the correct answer. All right. Okay, number 10. Which could be photosynthesis? So step 1, I have to identify, is photosynthesis a reaction that would be endothermic or exothermic? And Miss Ryan, was it endo or exo? Endothermic, because we are taking heat energy from the sun, storing it in sugars. So we don't want it to just be kind of stored. We want lots of energy stored. So which reaction is the most endothermic reaction? So we have 2 endothermics to pick from. Still A, yeah. And my uncomfort with the same letter being chosen 3 times continues, but it's still correct. All right. The most stable products, if you've been doing reading along with us, you know that the most stable products means the lowest energy level. And products would be on the right side. Right, 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 and right. And so I'm going to read the graph and identify, Ben, which of the 4 graphs has the most stable products? B does, because they have the lowest energy level, making them the most stable. All right, number 12. Trevor, log burning, endo or exo?
Exo.
Not just hot, we are on fire, so we are very exothermic. And which reaction is the most exothermic?
B.
B is. And apparently this worksheet really likes to use only 2 graphs. All right, number 13. Cade, number 13 requires us to do some math. I see that they've used the verb release. Is that going to be endo or exo, Cade? Exothermic. Which reaction released 50 kilopascals to the atmosphere? D as in David, right here. The difference between the reactants and the products is 50, and it is going out. Right? This one, the difference is also 50, but the energy is going in. And here the difference is almost 300, and here the difference is 50 versus 250, so the difference is 200 going in. All right. The greater the change in energy, the harder it's going to be for the reaction to occur. So we're kind of making this assumption. Yesterday we talked about collision model. It's kind of like being at a dance in middle school. So first, slightly awkward, right? And then the other part is it's like all of the guys are on this side of the dance floor and all the girls are on this side of the dance floor. Who's with me on this? Like you can relate. You can visualize this with me, right? Just nod your head.
Yeah.
All right. So the first thing is like the guy and the girl, one, have to actually see each other in order for a reaction to happen, right? If I'm looking at my phone the whole time and someone's looking at me, still not going to see it, no collision, right? Ineffective collision. Then it's also about the correct orientation. If I thought of clapping my hands as an effective reaction, is this an effective reaction?
No.
No, right? And if my goal of a reaction is to clap my hands, but I do it like this, then energy still makes a difference, right? And if I put a catalyst in there, Ryan, pop your hands for me, or put your hands like this. The catalyst is doing this. It's like making your hands clap, okay? So when we think about can a reaction be reversed, I'm looking at how much energy do I have to overcome in the reverse direction. So here, in order for the reaction to happen, I'd have to overcome 250. Here, in order for the reaction to be reversed, I only have to overcome about 100. Here, there's this huge jump. And here, there is a jump of 50 to like almost 200. Which of them would be the hardest to reverse, Doug? Which one? B as in boy. B as in boy. The hardest to reverse because it has the greatest jump. It will require the most energy, therefore be the hardest to reverse. All right, almost done. What is the activation energy of the forward reaction in diagram B? So let's ask Zach Yoakum. What is the activation energy for the forward reaction in B?
100 kilojoules.
Very good. 100, and the label actually is kilopascals. Kilojoules would be a unit of energy as well. I'm just going to read it off of the graph they gave between kilopascals. All right, number 16. Which reaction absorbs the most energy in the reaction? Nathan? It would be A. It has the greatest jump in energy. And then number 17. Which reaction has the most energetic activated complex? Bailey?
B?
Yeah, if you said that it was a tie between A and B, it's really, really close. I think B is on the line versus A. It's slightly below, but if you said, assuming that they're the same, okay, you got B. All right. Okay, so let's talk about, in here we keep making the statement forward reaction and reverse reaction. And it's kind of like, what's going on here? So I have my Florence flask, and if I make observations about the solution inside of it, Josh isn't here, Dejan, how would you describe the solution inside of this flask? Clear? All right. So Allie, put your thumb on the stopper, hold the bottle and shake it.
Oh, I can't see it. Oh, it's blue.
Whoa, it's blue. It's still blue.
Oh, it's getting clear again. Blue.
Blue. Okay. All right.
Actually, everything is reflecting off.
Oh, it's getting clear. It's gonna get clear.
Hold it for a second. What's happening to the color, Trevor?
It's clear now.
It's clear. Shake it. And now it is.
Keep shaking it. Keep shaking it.
It's just gonna. It can only become as blue as it can become.
That's pretty blue though.
Blue. Fair enough. Agreed. Pretty blue. So inside of this bottle, there is a reaction occurring, and when one product is present, the solution turns blue. When the solution reaches equilibrium, it shifts back, and it forms a reactant, and the reactant is in solution, and the solution turns
Blue.
clear. And then I shake it, and I push it back this way, and then it uses it all up, and it shifts back. And it is a reversible reaction. Now, not every reaction is reversible. There are a couple of rules about what makes something reversible and not. Okay? So in your packet, I want you to let it set. Once it becomes clear, we can shake it again. Okay, we're going to go. So not all reactions are reversible. Are all reactions reversible, guys?
No.
So there are a couple of rules. So let's look at some of those rules. I'm going to go into the packet. I'm going to flip to the page that says Equilibrium, Chapter 18. Equilibrium, Chapter 18. Today's date is 5/10. And the truth is that most reactions are irreversible. That is, they go to completion in one direction, and that is true if what they make sticks together. Okay? So most reactions are irreversible, or they go to completion if they make something that stays stuck together. For example, if I create a gas, the gas has left the system. It cannot reform with something in the system because it's gone. So if I make a gas, it's not reversible. If I make an insoluble product, like in our solubility table, on the back of our periodic table, if something in here says insoluble, and then it's not going to go back into the solution, it was insoluble. So that's irreversible. Or if a molecular product, a molecule like water, is formed then it's not reversible. I can't push the system the other direction. So those are 3 examples of when solutions are not reversible. Mr. Cabela, give me one of them. It is not reversible if a gas is given up. Mr. Yoakum, if
Insoluble product.
good, something that is insoluble is formed. And Trevor, if the third one, a molecule. You got it. A molecular product. I made a molecule, therefore this is not going to be reversible. Okay? So those are the 3. Now, some reactions are reversible. Some are reversible. That is, that the products, once they're formed, can react to yield the original reactants. We indicate this with arrows going in both directions. And we read it that A plus B in the forward reaction makes C and D, but we also recognize that C and D can react to make A plus B in the reverse reaction. So when we read left to right, we call that the forward reaction, and when we read right to left, we call it the reverse reaction. Whichever one is more favored is the one that's written as the forward direction. You're never going to need to figure that out. Just it's an assumption that I want you to make. However, it's written, whatever is first is the most favorable reaction, but we can show how reversible it is. Here the arrows are equal, so we would infer that it's both equally able to go forward and backward. We also can draw it with arrows that are unequal to indicate the forward reaction is more preferred or the reverse reaction is more preferred, and these are just little half arrows like when we did electron configuration, because it's a little messy than making 2 full arrows. Okay? So if A and B is forming C and D, as fast as C and D is forming A and B, then the reaction is at equilibrium. And this is a little fuzzy. Well, like, what does equilibrium actually mean? There you go. Shake it up. I'm on stopper. This blue bottle experiment has to be one of my favorite demos.
What two solutions?
What 2 solutions are in here? A distilled water, potassium hydroxide, and dextrose, which is a sugar molecule, and indicator solution that changes color. Yeah. So neat. And clear again. All right. There's this word, equilibrium. My children love to throw this word at me. That's not fair. Why wasn't it fair? Because it wasn't equal. Who's ever used that logic before? It's a favorite in my house. I think it's something about having children, right? So-and-so got this. That's not fair. And I will tell them repeatedly, and I'm going to tell you that fair does not mean equal, and equilibrium in chemistry does not mean equal amounts. Equilibrium does not mean equal amounts. And that's a key, that's like a big idea here, guys. Equilibrium does not mean equal amounts. Which is, you're like, okay, fine. So then what exactly does equilibrium mean, Fisher? If it doesn't mean equal amounts, what does it mean, right? And so I'm going to need 2 non-volunteers to help me. I'm going to draw sticks. Yep, 2 non-volunteers. 1 and Jaden Cabela and Cade Tickle. My 2 non-volunteers, you will both need a lab coat from the wall. Rotate. All right. And so we've got Jaden and Cade in the back of the room. Oh yeah. And what I need you guys to do for me is if you're in one of these front 2 rows, grab a chair in the back, grab a stool on the outside. increasing in volume and one is decreasing in volume, we are showing that the reaction in this direction is favored, meaning the reactants are being consumed, the product is being formed. Agreed? All right, let's do 10 more. There you go. Alright, scoop your butt your cup full for me, Jaden. Are you right? What's happening to the amount that you can place into your beaker? It is less and less. Alright, 10. Let's do 5 more. Alright, now, Jaden, I want you to scoop yours full. Kate, I want you to empty out your beaker for me. Alright, hold your beaker up, and Jaden, pull the water in your beaker into Kate's beaker. So, Kate, flip your beaker over. There you go. Pour it in. What was the correlation between what Jaden was scooping and what Kate was scooping? It's the same now. We have reached chemical equilibrium. The rate of change is the same. The amounts are clearly not. But the equation or the reaction has reached chemical equilibrium. Now, if my job is I'm a food scientist and I want to prevent this reaction from happening, I'm going to need to figure out a way to push the equilibrium this way. Or if my job is to maximize a reaction for an industry and I need all of this to get used, I need to figure out a way to push the equilibrium that way. So equilibrium does not mean equal. Just like I tell my children, fair does not mean equal. Equilibrium does not mean equal. Equilibrium means equal rate of change. Alright, perfect. So you can say step down, wonderful job. You guys head back to your seats. On your paper, I want you to write down what chemical equilibrium means. So go ahead and I'll write it down. Your pleasure.
I don't say anything
You're
about
supposed
you,
to write it?
buddy.
On your paper.
Sure. Where?
On your paper.
Since you're acting all Canadian.
On
Hey,
that
buddy.
chemical equilibrium change.
Okay, guy.
We're just not.
Shower pocket.
All right.
Really need one that's
Here we go.
She's recording it.
I am recording. That is correct. At the bottom of your paper, equilibrium does not mean equal amounts. Chemical equilibrium means the rate of change between the forward reaction is equal rate of change for the reverse reaction. Chemical equilibrium does not mean equal amounts, it means equal rate of change between a system.
Wait, what is that? It says forward what?
Chemical equilibrium means the rate of change between the forward reaction, reaction,
That's
is equal to the rate of change for the reverse reaction. So it's not the amounts that are the same, it's the rate that they are either forming or decomposing back into their original products. equilibrium is established, the concentrations of the reactants and the products do not change because the amounts stay the same because the rate is constant. So I can describe chemical equilibrium mathematically because I can measure concentrations and understand that at equilibrium those concentrations won't change. If I have a larger volume, I have more moles. If I have a smaller volume, I have fewer moles, and the concentration is constant. Right? All right. Thumbs up if you're with me so far. Okay. As chemists, it's important for us to understand the theory of what's happening. So we take a moment and we describe the theory of what's going on here. We recognize that there are different types of reactions as well. There are reactions that are homogeneous and reactions that are heterogeneous. If we flip to our vocabulary page at the front, we have homogeneous reactions and we also have heterogeneous reactions. Turn and tell your table partner what those prefixes mean. Same and different. All right. We are in $5.99 and page 600, chapter 17. Note, we are in chapter 17. Yesterday we talked about the collision model for chemical reactions and we defined the reaction rate. We listed 4 factors that can affect rate when we used energy diagrams to explain how a catalyst or affects rate. So check and check. You should be reading the assigned readings, 17 section A and 17.1 section B. And then we compare homogeneous and heterogeneous reactions in 17.1 section C, which is on page 599 and 600 of your textbook. A homogeneous reaction involves one state or phase, one phase, like all solutions or all gases, whereas a heterogeneous reaction is going to include multiple states reacting. So in a heterogeneous reaction, we have 2 or more phases, like hydrochloric acid solution and zinc solid, creating hydrogen gas and zinc chloride solution. This would be a homogeneous reaction, and water, H plus OH minus, making liquid water would be an example of something all in one phase because this is all in solution and these are in solution and solids. So we do recognize that there are 2 different families of reactions and we've been working with both of them this entire semester. We just formally defined them now. So we understand that reactions can speed up, but ultimately equilibrium does not matter on how fast we get there, because once equilibrium is reached, the rate of change is the same. It doesn't matter how fast I get there. Once equilibrium is reached, we can scoop faster, but equilibrium doesn't change. Agreed? Okay, so we can change how fast we get to equilibrium, but once we're there, then just heating it up isn't necessarily going to make a difference. But as a chemist, my job is to figure out how to either slow down something, like the oxidation of metal on your truck, or speed something up. And so we are going to investigate how we can stress equilibrium. How can I push the equilibrium to favor one side of the reaction, or how can I push it to favor the other? And so we're going to do an investigation in lab today, and we're going to do just that. We're going to stress equilibrium solutions. You grabbed the lab packet when you came in. I need you to grab that paper out, lab sheet. On the counter when you came in, there was a lab sheet. It looks like this. A study of chemical equilibrium. All right. So, we have your packet. Grab your science notebook. There are 3 equilibrium systems. We are going to investigate and stress 3 equilibrium systems. The first equilibrium system is a saturated sodium chloride solution. The second equilibrium system involves this indicator. The indicator has a big, long, fancy name. It's bromothymol blue. And in one form, it has a hydrogen stuck to the bromothymol blue. And when placed in water, and when we place this indicator in water, it will form hydrogen ions and a bromothymol blue ion. Now, I can write a hydrogen ion as H+, or I can write this as a hydrogen stuck to water. These are the same thing. We call this a hydrogen ion, and when it's in water, it actually sticks to water itself, and it's called hydronium ion. Okay, so those are the same thing. This is the indicator. It's a big, long formula. We just abbreviated BB instead of writing its actual chemical formula. Okay? If the solution favors this side, the solution will be blue in color. If the equilibrium favors this side, the solution will be yellow in color.
Wasn't that a question on our test?
Yeah. And yellow and blue make what color? And when it is transitioning between these two, you may see your solution turn green for a moment. When it's reached equilibrium, it's either going to favor this side and be blue, or it's going to favor this side and be yellow.
I remember you said something about that.
Mhm. Yeah. This is a 3, H3O+. Yeah. I didn't count it. I threw that question out because we didn't do it. All right. Okay, so equilibrium system 1 is a saturated sodium chloride solution where I have sodium chloride saturated in solution forming ions and forming a crystal solid, and that's an S, solid. My second solution has this indicator in water. When the indicator is favored, it's yellow. When the ion is favored, it's blue. And the third one is made with an iron compound. So the iron compound, there are iron ions in solution. And this complex called thiocyanate, which is a polyatomic and listed on the bottom of your polyatomic list, SCN-1 thiocyanate. And when it is in equilibrium, it makes this complex FeSCN plus 2. When this side of the reaction is favored, the solution will be red. When this side of the reaction is favored, the solution will be a pale brown. So I can, at equilibrium, I have equal amounts of these ions forming this compound, which is then breaking apart, forming this, which is forming that. And the equilibrium may favor this direction. So at equilibrium, it's possible that this may be the color you see the most. But what happens if I add something to the solution? Will it shift equilibrium? And if it does, what direction will the equilibrium shift? Okay, so at equilibrium, I have sodium chloride salt crystals and ions. If this side of the reaction is favored, it's going to look like water. If this side of the reaction is favored, what will I see forming? Salt crystals. If this side of the reaction is favored, what color will it be? If this side of the reaction is favored, what color will it be? All right, if this side is favored, it will be, and if this side is favored, it will turn yellow brown. All right, now the question is, how do we do this? Like, how do I shift stuff? I have to be able to add ions that are in these reactions in such a way that I increase their concentration. So where am I going to get the ions from? For this reaction, you're going to add hydrochloric acid. If I look at the reaction of interest, which ion am I adding when I add HCl? I am adding chlorine. That is the ion of interest to this reaction. Now, there's hydrogens there too, but no problem. They just hang out. They're not included in this reaction, and we don't care about them. Okay? In the second reaction, the first thing I'm going to do is I'm going to add hydroxide. I'm going to add sodium hydroxide, which means I'm going to add hydroxide ions. If I add hydroxide ions to this reaction, tell your table partner what could potentially happen. If I add hydroxides to that reaction, what could the hydroxide potentially do?
Like another water.
React with hydrogen. Yeah. Instead of H3O, I get
H2.
H2. Okay, so if I add sodium hydroxide, I acknowledge that the hydroxides are of interest. They will react with H plus to make water. All right, if I add HCl, then which ion of interest am I adding? Is there any Cl in this reaction?
No.
Nope, so now I'm adding H plus. If I add H plus, something's going to happen, right? So we're going to do this 3 times. We're going to add OH, and we're going to see what happens. Then we're going to add HCl, which means we're adding H, and we're going to see what happens. And then we're going to add OH again, and we're going to see what happens. Maybe. We'll see. Okay? And then for the last one, go ahead and on the back of your paper, go to letter C, where it says iron 3 thiocyanate equilibrium. And I would like, let's have, I keep calling the same people. Sierra, will you please read number 1 here for us? KSCN. All right, if the color is still very dark, add more water. So you should be able to see through it. Okay, so it's going to be colored, but if you look through the edge of the beaker, you should be able to like see through the solution. And all right, and it'll make sense when you get there, right? Place 3 4 cubic centimeter portions of this solution in separate test tubes, and these are the 3 test tubes that you're going to do your reactions with. So you have to make a stock solution first, and then you're going to use that stock solution to run your 3 tests. And you will add 10 to 15 drops of FeNO3 to 1. To the second test tube, you will add 10 to 15 drops of KSCN. And to the third test tube, add a few drops of 6 molar NaOH. Note, the FeOH3 that forms is nearly insoluble, which means it may look slightly cloudy, or, yeah, slightly cloudy is probably the best result that you're going to get, or there'll be a color change. This is what your job is. Make careful observations of the test tubes. Record the original color, note any changes, and when done, rinse the contents down the drain using plenty of water. Do as you order, add acid to water, turn your sink on first, solutions go down the drain, wash everything with soap and water, and return it to, there is a container for your test tubes in the back. There's a box for the test tubes to be washed and dried. They don't have to be dried, they have to be washed. You can place them into the box. The styrofoam trays I've set out for you go into the Rubbermaid tote. Thiocyanate is a hazardous compound, so we're going to make sure that we are not bringing any water bottles, food, gum with us into the lab today. We're washing our hands with soap and water and wiping down our lab stations before we leave. Your job is not to figure out what's happening. Your job is to figure out what you see. We'll talk about why it happens. Okay? Each lab station is set up to work as a team across the lab station. So when you're done with one reaction set, you'll go to the opposite end of your lab station and trade with that table team and do the other set and vice versa. Questions? Record everything. Take your science, your paper and your pencil. Take those observations into the observation box. I'm going to start a timer for 30 minutes to guide your time. Yeah. Yeah. I did, but I think I missed it because I didn't do it so much.
Okay. Well, he was still on. I substituted. I told me and when I went down there, they said, I was just curious.
Yeah, is he going to be here tomorrow?
You should. Yeah. I think it was just something to do with
Oh,
something. I don't know what it was. He took over.
Goggles on at the beginning of lab. You have to read your lab protocol and be very intentional with your lab measurements.